and then the metadata for each of these are included. So to compare the dataset to current relevant novel datasets, so we've got BODMAS, Ember, SOAR L20M, and Microsoft. I know a couple of the authors for these datasets are here with us today. I'm amongst giants. But to compare our dataset to these ones, likewise with these datasets, we include threat details and family details, and these are classified using tools like AV-class in our dataset. But as well as that, we include the vectorized features of the vulnerable samples, vulnerability details. So these could be information about like CWE, which is further down, the vulnerable payloads, the packer types and complexities, which I'll get into, and the MITRE attack techniques. So quite a lot of information to pack into the one data set. And as everyone who's worked with labeling data, it's very hard to label every sample itself. So there are some empty samples in there, but hopefully later down the line that can be remediated by update tools or better samples or the likewise. So there is a slight concern with the trustworthiness of the non-vulnerable label. So with the vulnerable label, it is not assumed. We know it's vulnerable because it includes a proof of concept. And that proof of concept is given within the dataset. So that is an exploit of the code behavior or path. And these are obtained from PEVuln and ExploitDB. So PEVuln is a database set up by a researcher called John Page. And he essentially exploited all these malware samples and put them within a database that was able to demonstrate across all these samples ranging from early 1990s to contemporary. And then everyone knows ExploitDB. ExploitDB hosts tons of software that is also vulnerable based on proof of concept exploitations. As for the non-vulnerable samples, with our non-vulnerable benign samples, we obtain these from a fresh installation of Windows 10. And you would assume because of it being a fresh installation that a lot of these executables and DLLs would go through rigorous testing by the security team at Microsoft. And then for the vulnerable, non-vulnerable malware samples, we used what's called static application security testing. And there's a few tools out there like CV bin tool and Vuln scan. So these tools will scan through executables and try and find common code or slices that are vulnerable to compare against other samples. And they'll give you a common weakness enumeration based on that too. So once we found out that some samples were vulnerable by the tools, we removed these from the data set before training the machine learning classifiers. And then we also ignore 0 days. So another thing I want to point out is even though we provide only the Ember features and not the actual samples itself for each class, the data set can be used for a lot more. So we do provide in the metadata the hashes of the samples so that you can, as a researcher, go out and obtain these samples yourself very securely, work it in a sandbox. It is malware, don't run it on your machine. But you can obtain these samples yourself and use them for your own research. And that can be for anything. You can use it to demonstrate new exploitations, find new vulnerabilities within malware. If you do, brilliant, let me know. I can whack it in the data set because that'd be really helpful. But yeah, there's a lot more you can do with this rather than just using the Ember features itself. So going on to the next slide. We used the paper by Xavier Ugarte-Pedrero called SOK Deep Packer Inspection. So within this paper, they present a comprehensive taxonomy of packers, and more specifically runtime packers, and develop a framework to analyze the complexities of these packers. So the complexities range from type 1 to type 6, where as the value increases within the type, the complexity of the packer also increases. So we were able to come to a conclusion that there was the same pattern across vulnerable and non-vulnerable malware samples, as you can see. So there's that overlap between the vulnerable and non-vulnerable samples means that we can develop classifiers that do not associate specific packers to the malware types. So in other words, obfuscation shouldn't really be an issue when we're training these machine learning classifiers to classify whether or not a malware sample is vulnerable. So there's a lot of analysis that we've included in our paper about this topic, but that's generally what we came to. Additionally, we include a lot of vulnerability mapping. So In our case, we use common weakness enumeration, and we have a giant table in our paper. For purposes like this, I'm not going to put the whole table in because we'd have to make a bigger screen. But for the malware samples, we can see that the highest count so far is CW275, which is permission issues. And within that, you can assume that these malware samples have issues with the hard-coded authentication within the samples itself. So if you think like ransomware or botnets having hard-coded values or permission issues, it means you can route back to the C2 server through that sample itself. It could be connected to it via an unauthorized channel or so-and-so. As for the benign samples, massive jump from the second to the first highest, nearly 10 times. But CW119 is the most prominent CW within the benign samples, which is improper restrictions and operations within the bounds of a memory buffer. So what this essentially says is it's similar to a buffer overflow. There is certain out of bounds with the memory that you can then utilize for code execution or to crash the application itself. So say this was a firewall application, a malicious actor would like to crash the firewall or proxy in order to gain access to the system. Additionally, there is also MITRE attack mapping to the vulnerable malware samples within the data set, and we go into a lot of detail with this as well in comparing it between each sample. And then this is the metadata details. So as you can see, we include hashes, timestamps. So in our case, the first seen timestamp for VirusTotal reports, the type of malware, so the type of threat, vulnerability, description about that. So within MalFun, there's a wide description about that malware sample and how it's executed or exploited. That's also included as well. The type of family, vulnerability IDs. So you can think MVID for the vulnerable malware. As for the vulnerable benign samples, you have things like CVEs and OSVDBs, but I think open source vulnerability database is now deprecated. Correct me if I'm wrong, but we include it anyway. And then as well as that, a lot of Packer information that we obtained from a tool called Detected Easy or DIE. So just the setup of our model. So we have the executables running through the Ember feature extraction pipeline. And these factorized features are passed through common machine learning-based models that we'll explain later or after the slide. And then we perform rigorous binary classification and multi-class classification on these samples using default parameters, hyperparameter optimization, and stratified k-fold because of the imbalance in data set sizes, just to see if we can rule out any imbalanced results. And as you can see, the accuracies are quite high. For the LGBM model, we were achieving an accuracy of 0.96, and then the other models following closely behind. As well as that, within the binary classification, still obtaining results above 0.9, which we thought was very good. So there's more analysis on the results in there, as well as the other tables that you can compare. And these are just benchmarks. So if anyone wants to go in through and use this data, they have machine learning benchmarks that they can base their models off. So the contributions is a curated data set with a lot of annotations and vulnerable samples that researchers can mess around with and try and use to exploit other malware samples. As well as that, we've got benchmarks for the machine learning models that you can utilize. And we also use the state-of-the-art Ember features. So for the future work, obviously, we want to expand the data sets. It's too short right now because of reasoning. But there is future research in which I'm also doing myself to try and expand on the data samples. As well as that, it'd be interesting to utilize CWE chains. So CWE chains are vulnerabilities that are linked together. So you would expect a low-level CWE within the chain, once exploited, will carry on through the chain and hopefully heighten the vulnerability or exploitation within that sample. So it could be as simple as, knocking off a bit of software to user access privileges or escalations. Identifying novel vulnerabilities. So there could be vulnerabilities in the samples currently that haven't been explored or found. It would be good to try and find new vulnerabilities that could be added to a corpus within the data set. And finally, improving the trustworthiness of the non-vulnerable label through techniques like behavioral analysis by fuzzy testing. So like in the DEF CON video previously mentioned, and similarity analysis between the samples. So that could be similarity between the code or if you were to hash the code and compare similarities between that using things like TLSH and stuff. So just a quick note of the acknowledgements. So we're funded by the Department of Science, Innovation and Technology, by Innovate UK and the UK government. And then one of the other authors, Dr. Carlin, is funded by the UKRI at EPSRC. So that is everything. I've also thrown up a link tree there in case anyone wants to add me on LinkedIn or anything like that. It'd be great to chat to you. If there's any information you'd like to know more about the data set, send me a message. But yeah, or if you want to shout at me for helping the hackers, then go ahead.
Okay, we will open it up for questions for Nathan. I will kick us off with an initial question, possibly because I missed the first couple of minutes. But could you talk a little bit about what the intended use cases of the data set are, or the classifier that you described? It's really interesting. I haven't really thought that much about vulnerable malware before, so I'm curious to hear your thoughts.
Yeah, so the use case is more for offensive security, whether it be in a company who has critical infrastructure or to defend against hackers trying to infiltrate like the NHS, for example, or any type of use case, even if you're working from home and you've got your personal computer and you've accidentally clicked on a phishing link or something, to be able to get these vulnerabilities, or not vulnerabilities, these malware samples on your computer, and for a malicious actor to be targeting your company or yourself, it's good to use a different technique rather than trying to protect against it, to be ready to fight against it after it's on your system already. So it's just another defense mechanism that's being implemented. But yeah, so it's a really interesting take on it.
Hey Nathan, great talk. I have two questions. So we also worked on an AI for malware detection and classification.
Mm-hmm.
And in our data set, we increase the number of malwares so that the model learns more about the malware samples than the benign samples, and had upsampling to like address the imbalance issue. Versus you, in your data set, I see that you have more benign samples than the malware samples. So how is that working? Like, is the model giving better accuracy? And why are you using that? First question. Second, is the model language agnostic? Like, can it detect a malware in Python or Go language as well, or just to a specific language?
That's very interesting. So the first question about oversampling and undersampling. So I did a little investigation with the data set using Smote. And with that, I was able to oversample the data. Now, I probably have done it wrong, and I probably didn't look into it much, but it actually decreased the accuracies of the model itself. So it could be something to do with affecting the actual information caught by samples. So if you're oversampling certain samples, you wouldn't think of like some sort of generalization problem within the model itself, but it could just be that the data was changing so much that it was unrecognizable, specifically within the vulnerable, that it was maybe misclassifying it as non-vulnerable malware. So I dropped that for now and tried to just work on increasing the sample sizes based on other techniques rather than oversampling. As for your second question, code-specific vulnerabilities. So you can analyze what type of code is used for each sample based on their compilers and linkers. So that information is provided in the data set itself. As for an analysis of it, I haven't done it just yet, but there are ideas that I have in place for doing that kind of stuff. Okay. Thank you very much for your question.
Presenter. So someone on the Slack is asking if, well, first of all, great talk, they say. Do you have a pre-pub version of the paper?
A pre-pub version of the paper, I do. But it is being dissected and ready for the camera ready. So I should have took a previous version of that and saved it. So I apologize. There is, but you'd have to put it back together again like Frankenstein. Okay. But the camera ready one should be hopefully done by the end of next week.
Okay, I'm sure it'll be worth the wait.
Oh, it's worth the wait.
All right, thanks so much.